Mesdames, Messieurs, c'est un grand plaisir, l'honneur pour moi d'être ici, de parler dans cet auditoire. Malheureusement, mon français mathématique est trop pauvre maintenant. Je vais parler anglais. The first, what I have to explain is the title of my lecture, Numbers as Functions. The lecture will consist of two parts, numbers and functions literally, and then when we have functions, then it's interesting what are constants. And it turns out that in the simplest and most basic sense, constants are roots of unity. But if they are constants, then how do we work with them? Okay, so the introductory part concerns two probably most famous and, in a sense, most important transcendental numbers, most important in particular for physics, pi and e. They are also very famous. When I was thinking about the history of these two numbers, I suddenly realized that the basic terminology classifying real numbers is, so the numbers can be, well, rational, okay, irrational, okay, transcendental, and imaginary. Each term which we now consider as a definition actually is an expression, a very emotional expression of bafflement of mind. Human mind have been discovering numbers, but each time when something essential happened, it was baffled by what it has discovered. And in particular, pi and e turn out to be two of the most famous numbers about which pretty much even something that can be called fiction or poetry has been written, but about pi much more than about e. E is much more transcendental or much more baffling than pi. Well, anyway, there is this famous, beautiful formula that you know. I consider it as the most beautiful formula in mathematics. E exponentiated to power pi equals to -1. And I could speak about 5 or 10 minutes about its history, but it's okay. But what is important is that it is so fundamental because, in particular, it is the basis of the quantum interference of not probabilities as one usually speaks in fiction or in popular literature. It's not interference of probabilities, it is inference of amplitude of probabilities, of course. And so the question I will be asking, this question and things around it, do such transcendental numbers as pi and e have also certain arithmetical properties somehow related to prime numbers? So rational numbers, okay, they are product of primes. Algebraic numbers, okay, they are products of something that generalizes the primes. So what about transcendental numbers? There are two quite non-systemic positive answers with respect to these two numbers again, pi and e. The first one is the famous formula for the value zeta of 2. And essentially this formula is adelic and not, because it refers to all primes together, and actually this is a formula that in some natural measure GL2 by GL2z, the measure equals to 1. The second story is that if one takes formally the formal series for e power x, so x power n divided by n factorial, if you put x equals to p, then it will converge periodically. This leads to an absolutely false but very tantalizing proof that e is a transcendental number. Namely, if you try to take the pth root of the right-hand side, it does not exist in QP. it will produce an extension of degree p. So this cannot happen with algebraic number. So how E can be algebraic? Now, this is tantalizingly simple and totally wrong proof, and it was so tantalizing that at first Hensel, who invented p-adic numbers themselves, has written it in his notebooks, but it's still unknown whether one can produce a real proof out of it. Even if there are students in this room, please try to find a mistake in this proof, first of all. Anyway, these two examples show that there is some kind of arithmetics behind E and pi and probably other transcendental numbers. Now, I was starting to think about this stuff in context of physics when Maxim Kontsevich and Don Sagir introduced a very important subring of complex numbers that contains all algebraic numbers and has a lot of transcendental numbers that are important in physics. There are certain Feynman integrals. So again, you know, or you had, that when you try to calculate certain important probability amplitudes in quantum field theory, you essentially get a formal series which also diverges, but let's temporarily forget about that. Its coefficients are generally some transcendental numbers as well. And so when I was many years ago invited by a community of physicists who are doing the so-called p-adic physics, I started asking myself, is there something like p-adic physics really? If we don't have p-adic E or p-adic pi, and we have a lot of Feynman integrals that produce a lot of transcendental numbers, also seemingly without arithmetic properties. So how can we speak about p-adic physics? First of all, formal definition of these numbers introduced by Kontsevich and Sagir. They are called periods. They form a ring denoted P. And the formal definition is this. We should separately define the real part and the imaginary part. And each of these two numbers should be a value of an absolutely convergent integral of certain functions. The functions should be rational functions with rational coefficients of a certain number of variables, doesn't matter how many, over certain domains. And the domains should be defined by polynomial equalities or inequalities with coefficients in Q. And the simplest example, pi. Pi is a period, and here is its formula for it as an integral. Okay? So facts that periods form a subring of C. If you take such a thing as value of gamma function at a rational number and then take its qth power, Q is denominator, then it's there. And Feynman integrals of a certain class are periods. Seemingly, it is not known whether pi power minus 1 or E itself are periods. Conjecturally not, but seemingly it's not known. At least I haven't seen anything proof. Now, in geometry, the word periods in algebraic geometry has been used to refer to very special and usually transcendental functions. What we do is that we consider algebraic manifolds defined, say, over Q, or algebraic extension of Q, and then we consider topological chains on them with good boundaries or even cycles, and then we integrate these forms over them. But we consider, we should not consider separate varieties. We should consider, say, universal families of such varieties or something like that. And then we will be considering these periods as functions on the coefficients defining the variety. And then we get functions. Well, this is the simplest thing. Consider a curve, a cubic curve. This is a Weierstrass form of elliptic curve, so one can compactify it by adding a point at infinity. It depends on the parameter t. And its Riemannian surface is a torus, two-dimensional torus. So there are two closed one-dimensional cycles. We can integrate the differential of the first kind on it along these cycles. It turns out that if one defines the result of such integration by omega, considered as a function of t, then it satisfies very simple kind of hypergeometric, not quite, linear differential equations. So those periods that are functions are examples of transcendental functions of transcendental functions that are solutions of some good differential equations. There is a little bit more interesting example connected with this story. Let us integrate from some fixed point, say at infinity that we added, let us integrate not over a closed cycle, but over any path from this fixed point to a variable point p. And it turns out that if you apply the same linear operator to this integral, then you get an expression which is almost rational function of x and y, of coordinates. In fact, it's rational function of x, y, and derivatives. And this rational function has a strange property. If you add 2 points on an elliptic curve, it is a very nonlinear transformation, then the result of calculating this function mu of pi becomes just simply additive. This plus is addition of points on an elliptic curve, highly nonlinear operator, and this plus is just the sum. And the explanation, as I said, is pretty simple, although non-trivial. If you apply this differential operator to this differential itself, then you get a total differential. This is just an exercise for students. And then using the formula of differentiation of the parameter, you get the stuff. So the first part of my lecture will be dedicated to a generalization or a very interesting version of this story invented by Alexandru Buium, which I will call, and he calls, arithmetic differential equations. Namely, the principle of his idea is, in order to see periodic properties of such transcendental numbers as periods, one could try to design a theory of derivations in the periodic direction. So instead of dependence of actual variable t, we imagine p as a variable, but then try to develop calculus where you could differentiate in the periodic direction. So if I were to speak before physicists right now, I would say that I'm considering a theory that might possibly have application to periodic physics, where periodic is only time. Everything else is as usual, but time is periodic. Let's see how it can be done. It's not at all obvious that it can be done at all, and Alexandru Buium, who worked for 20-25 years on it, in abundant series of work, has proved that yes, one can do that. So let's consider very attentively the following table of analogies. So instead of just general functions, we are considering at the left-hand side formal series. So for example, if you have an analytic function of t, then near a point it is a formal series. So let's consider its local avatar. the periodic analog is either just periodic number, or we will be consider generalization of it. We will consider what is called in number theory maximal unramified extension of periodics, or just integers in these periodics. Maximal unramified extension means essentially that we add all roots of unity of degree prime to p. That is the simplest description. So here, coefficients are taken from some field of constants, whatever you choose. If you wish to work locally with usual analysis, then coefficients are just in C. But here, that's a very strange story. Usually when one considers a periodic number, one imagines that the first coefficient is some representative of the number modulo p. Then you delete it, let's say the second coefficient is some representative of the resulting number modulo p squared, something like that. But actually, then you lose all algebraic properties of k. There is no addition, no multiplication. In fact, it turns out that if you choose as representatives these roots of unity that are in this field or this here, then at least you lose addition, but multiplication is still there. So let us represent periodic numbers in this way, where epsilon I are those roots of unity that are here in this ring or this ring. They are called Teichmüller representatives. Now, the first central, so this is the first central fact. The second one, Bouillon suggests to consider, instead of derivation d by dt here, the following operator, which he calls delta p, and considers as derivation in periodic direction. So the most non-trivial part here is the operator phi capital. What it does is this: he takes every epsilon I and replaces it by its pth power, epsilon I power p. And then one can take the power p of the whole number, then one can take the difference, and then divide everything by p. This will be Bouillon's periodic derivation. Okay. Now one can define polynomial differential operators. In the classical case, if you have, say, some polynomial with variable coefficients f, polynomial depending on some additional variables t0, t1, tn, and so on, then one gets an operator acting on functions. You take this polynomial, you take variable function of t here, you construct all its derivatives, f prime, f power n, and then you input into this polynomial. So this is a nonlinear nonlinear differential operators, and if a function depends on many variables, for example, no problem at all. You include derivation, partial derivation with respect to any variable, and get this thing. Now, what is analog here? The first very important difference between here and here is such. So, of course, you take R, this is analog of periodic series, of formal series, then you take polynomials, but then you take a certain completion of this ring. It's not just a polynomial, it can be an infinite sum of polynomials with coefficients that periodically tend to zero. Periodically tend to zero, so that you get something that is a periodic completion of this ring. But otherwise, you announce that partial differential operators acting on numbers, on periodic numbers, are maps of this kind. Are maps of this kind. Okay. And first of all, it's not clear at all why it is non-trivial. And for example, the first example, which is not quite obvious, periodic logarithmic derivatives. In the usual case, if you want to convert multiplication of functions into additions, you say, okay, let's take logarithmic derivatives. Logarithmic derivatives of a product is a sum of logarithmic derivatives. It turns out that generalization of the story exists here as well. Multiplicative group of periodic numbers or integer periodic numbers maps into additive groups if you apply this kind of power series. It involves only delta p of A, so it is a differential operator of the first order, periodic differential operator of the first order. And it is an infinite series. Remember that I allowed it growing powers of p multiplied by something. But it is additive. It's not difficult to prove. It's okay. Example 2, quadratic reciprocity symbol. That's for number theorists. This quadratic reciprocity symbol from Gauss time, a little bit earlier. It's something that is equal 1 if A is a square modulo P, or minus 1 if A is not a square modulo P, something very discrete. It turns out that it is actually given by differential operator of the first order again in the sense of Bouillon. So there is such a formula for this. Example 3 is much less trivial, much less easy, say, and that was actually probably the first paper by Bouillon that actually attracted attention of a lot of people of number theorists. It was analog of this function that when applied to points of elliptic curve, depending on parameter t, becomes additive, as it was in commutative case. And he invented such a function. I cannot write its explicit expression. I haven't actually ever seen it, but it's proved by using quite deep algebraic and arithmetic geometry. So there exists an operator of the second order, periodic differential operator of the second order, that produces such analog of this stuff. Okay, there is also example of periodic differential operator that is constant on isogeny classes, but okay, I will not be dwelling upon it. The question C, is there a global version? Okay, periodic numbers are like power series, formal power series. And say integers are like polynomials, say, of one variable. It's a very long known analogy. Integers are polynomials of one variable or something like that. And there are many primes involved in this story. Can one say something about this case, which is not formal but kind of elementary functions at first, like polynomials, and then one would like to do analysis, calculus? Does there exist? Yes, one can consider all such operators for Z, for example, as a set of partial derivatives, but taken with respect to various points, say, over Riemannian surface or something like that. And if one wants to apply it to some more complicated ring than Z, you consider it as eventual field for arithmetical calculus. Okay, the only thing that one needs for this R is what is called lifts of Frobenius, such ring endomorphisms that modulo P produce A power P, and then we can just may put like that. Okay, and it turns out, and it was understood no more than 10 years ago, or something like that, that actually rings with such structure, admitting lifts of Frobeni, appeared in totally different contexts. Some time ago, actually, Grothendieck introduced them and called them lambda rings. there are two slightly different, two definitions which are almost equivalent but not quite. A system of psi operations on a commutative ring is something which is essentially a system of lifts of Frobenius for all primes, but then you just formally multiply them by using multiplication of primes. So catchword, psi operations are a family of coherent lifts of Frobenius endomorphisms. And there is another definition which is called lambda operations on a commutative unitary ring. They are just system of additive group endomorphisms. These are formal properties. So here only addition is involved, but at the right-hand side, multiplication and addition is involved. And Grothendieck discovered a lot of fundamental examples coming from algebraic geometry of lambda rings. But then there was no idea that it can be used in some kind of arithmetical analysis. That was very recent. And these two definitions are almost equivalent in the following sense, that if A has no additive torsion, then these two notions are essentially additive. This is how to reconstruct from psi operations lambda operations. And generally, even without this condition, if you have lambda operations, then one can define psi operations. So this ring is called the lambda ring. Okay, and here is one of the examples. This is the typical Grothendieck construction. If you consider the Grothendieck K0 group of objects of this is K0 group of a category whose objects are a module and an endomorphism. And here is how do you multiply them, and here is how you define lambda k, then you get this stuff. And there is a second example which was invented in number theory and is called big Witt ring. And that's very funny. So if you just take any commutative unitary ring, and then you say that for big Witt ring, its additive group is multiplicative group of power series with coefficients with R. Here is how you multiply them, and then extend by distributivity and continuity, and here is how you define the lambda operations. So it's a very interesting set of examples, showing that the same objects now converge from various sides of mathematics and kind of produce some tentative answers to questions that was asked by physicists. Does there exist a p-adic physics? Does there exist an adelic physics, probably even? Adelic physics in which pi has nice arithmetic properties and things like that. Okay, now I will pass to the second part of this lecture. Let me return a little bit back. So you will remember that I told you already that when you are considering power series, coefficients are constants, k. When you are considering p-adic numbers or something like that, coefficients, it's best of all to choose as coefficients roots of unity. But if you can add numbers and not only multiply them, you cannot add roots of unity, you will not get a root of unity. You can only multiply them generally. Of course, you should add also 0 to it. So this is what is called a monoid. It has one operation, but not two. So natural constants in the theory I am considering are at least roots of unity, or probably more general monoids. So now I will pass to the second part, which is the project of creation of algebraic geometry, constants for which would be roots of unity. It's very funny, but it was also related to early stages in physics and then to quantization. I will show you how. So just formal notation of this non-existing geometry was f1, or then later f1 power n, or even f1 power infinity. Because you may remember that, say, the field with p elements, where p is a prime number, is usually called fp. Then for any n, there exists its extension of degree n, it's called phi p power n, and so on. So here, seemingly paradoxical notation was invented before the objects were invented. Okay, so the subpart I is called F1 in search of a definition, a mathematical object in search of a definition. Of course, I borrowed this title from a famous drama, 7 Persons in Search of an Author. There was a heuristics that was very nicely explained in one of the founding papers of Jacques Tietz, that algebraic geometry over f1 power n is a limit of geometry over fq, q power pn, and p tends to 1. Of course, literally it cannot be so, because p is a prime number. How can it tend to 1? Nevertheless. And now we see that that story started much earlier and again has something to do with physics. If we want to pass from 1 to q, where now q is not necessarily a power of prime, just say a letter or some complex number or whatever, then we can introduce a deformation of integers, which is called Gauss q integers. Here is the definition of n deformed by q. Here is the definition of n factorial deformed by q. Here is the definition of binomial coefficients deformed by q. This invention was made before Kronecker had said his famous motto that integers were given by God and everything else was invented by man. I always tried to read it as the statement that integers are the only non-deformable object of mathematics, until I understood that, of course, integers are also deformable, and the Gauss has already made it. So this is a continuous deformation of integers. Very funny. For Q itself, there are two very different and very natural habitats. Namely, in quantum mechanics, which, okay, if you wish, you can consider it as physical interpretation of non-commutative geometry or something like that. You remember that after Heisenberg, one of the main objects in quantum mechanics, what quantum mechanics does, it replaces observables, which commute in classical sense, by non-commuting observables, operators. And since they do not commute, their commutator is 0. But it turns out that if you consider deformed commutator itself and put Q equal to quantum mechanical, the usual story, then in the sense of this deformed commutator, they become commuting again. So they are quantum commuting variables if they satisfy the Heisenberg commutation relation. And then, if they are quantum commuting, and if you try to write, for example, Newton binomial formula for it, then as coefficients you will get exactly Gauss deformed binomial coefficients. Very beautiful. Okay. And there is, of course, another habitat with which I started, that good values of Q are powers of prime. They are not at all similar to good values of Q that I considered before that. And, for example, the deformed ends appear as essentially the number of FQ points in the projective space. And if you want to consider the number of FQ points in a Grassmannian, you will get the Gauss binomial coefficient. So here, then, you can also try to go here. So you can try to go in the inverse direction to make u equal to 1. And then here you will get the classical n and classical binomial coefficient. And Jacques Titz's remark was that if you decide that F1 points of projective space is just a finite set of cardinality n, then Grassmannian will be a set of subsets of cardinality j, and then all cardinalities agrees. So perhaps the geometry, algebraic geometry over F1 starts with just avoiding any additional structure on your projective spaces, just saying, okay, this is a set of a given cardinality. And Titz more or less formulated the program, makes sense of algebraic geometry over a field of characteristic 1, so that projective geometry becomes a special case, for Titz at least, of the geometry of Chevalier groups and their homogeneous spaces. And the first actual implementation of Titz's program appears after 10, 15 years of work only in 2008. Only the field of definition they need is F1 squared, not just F1. Now, what is F1 squared? I didn't say that. That was suggested in '94 by Kapranov and Smirnov. So they say, and now we come to the heart of my comparison. F1n is exactly this monoid, not just a set, but this monoid. And so, exactly the constants in the Bouillon story. They didn't read Bouillon at that time. They don't refer to Bouillon. So these two lines of thought converged sort of inadvertently. So in '94, I sort of stumbled upon non-existing F1 geometry by suggesting that one should try to imitate, I was not the first actually, but anyway, that one could try to imitate the old classical proof of Riemann conjecture for curves over field of characteristics P. To this end, one passes from curves to surfaces. One should take a square of a curve. And then there is a very natural algebraic geometric formalism that leads to the proof of Riemann conjecture. Can one do something like that for Z? And then what should be the product of spectrum Z cross spectrum Z, or if you wish, the tensor product of Z with Z over what? And my suggestion was that this imaginary object should be just this as F1. And I suggested that there might exist a category of motives over F1 that is partly visible through their zeta functions. And in particular, the zetas of what I called Lefschetz dual Tate motive L should be given by this polynomial formula. S, which is usually a very transcendental parameter, here is just like that. Then there was a very funny formula. You remember that in functional equation for zeta S, there exists a multiplier which is a gamma function. It is a transcendental function, not quite of the type that was considered in the theory of periods, but from this viewpoint, it looks like F1 zeta function of the infinite dimensional projective space over F1. And this observation is still not explained and not included into any general picture. So I still am interested in any ideas about that. Well, anyway, so it was, as I said, what I was explaining before was a kind of search of definitions of geometry over F1. And then during the next 10 years or so, definitions, probably even 8 or 7 definitions were found, but too many. Here is a land produced in 2009 by Lorscheid and Peña, map of various definitions, map of F1 land. So each point, each domain here is a definition suggested in one of the mathematical papers. You see now how flourishing is this subject among mathematicians. Each of them define a certain category that is supposed to be a category of schemes or whatever over F1. And then they are connected by a lot of functors. If you have a scheme in one sense over F1 and then in another sense, then sometimes there is a construction that produces the second type of F1 schemes from the first type. And this is a function. All of this is given by arrows. And then everything kind of finishes by moving each of these definitions to the outside, which is a large world of usual Grothendieck'ian schemes, algebraic geometry, periods containing interesting transcendental numbers that appear also in physics, and so on. This map by now, so it was 2009, by now it is already too old. The F1 land is now much vaster, but it did not become more united. It's a kind of European Union rather than United States of America. And the definition that I like most returns us to the first part of my work. Borger's principle is that if you have a ring A with a lambda structure, and you will remember that a ring A with a lambda structure is something where you can do periodic derivations for any P. So something which admits a very good analysis in the Bouillon sense for various P. And Borger's principle is that such a lambda structure is what should be called descent data on the scheme spectrum I of this ring to F1. So essentially, Bouillon's arithmetical calculus is the same as considering whatever you want to consider over constants F1 or F1 power n or something like that. Something very, very natural because they are exactly constants in Bouillon's story. And in particular, we now even have a candidate for this product, which I tried to introduce in order to try to find a way to prove Riemann conjecture. And now we have a candidate for it. It's something like that. Okay, everything can be globalized. I don't want to put too much strain by using a lot of technicalities. What I just want to say is that for me, this development of the last 20 or so years was extremely fascinating, partly because it's kind of was following the Grothendieck's dream and the development of algebraic geometry, which was my main subject when I was young. On the one hand, it followed it. It produced some very general definitions, but actually not definitions, but intuitions. You have very general intuitions, and then you try to squeeze them into a mathematical theory, axiomatized, defined strictly, and so on and so on. And the story is so fascinating because it's very far from being finished. Intuitions are still there, some definitions are still there, but not everything that you would like to do is there, and most interesting things that you would like to do are still not there. So it is a very interesting research field, especially for young and ardent researchers. And as I said, besides number theory and mathematics, algebraic geometry and mathematics in general, it has a lot to do with physics. If you only wish to consider simple quantum mechanics with parameter of quantization Q, or Feynman integrals in the version when their values are given by perturbation series or something like that, and you want to understand whether they have arithmetical properties, again, you should turn to this story. Well, I think it's reasonable to finish here. Thanks for your attention.
Questions?
Do you have a favorite among all the possible construction of F1s?
Yes, my favorite at the moment, at least, is burgers. Yes.
Other questions?
Well, as one used to say in Moscow, everything was crystal clear.
Okay, so let us thank Professor Yuri Manin.